Finite State Machine for String Matching by George Nash. String matching is essentially scanning a sequence of text for a defined pattern. For example, here we have the pattern P, ABAA, and we've successfully matched it within the sequence. This method of string matching has many real-world uses. For example, matching patterns of DNA, or more specifically to a finite automata approach, lexical analysis in a compiler. Let us first define a finite automata. It is a quintuple defined by Q, which is a finite set of states, Q0, which is a state within Q, that is the starting state, A, which is a set of accepting states, again from within Q, sigma, this is the finite input alphabet, and finally delta, the transition function. Let's apply this definition to an actual automata. This automata checks a sequence of text for the pattern ABCAB. As we can see, the start state Q0 is set to state 0. This is where the automata begins its processing of the text. Characters are read one at a time sequentially and are the input to the automata. A transition, seen on the image as a directed arrow between states, occurs by passing a state, for example AB, and the input, for example C, to the transition function and getting returned a new state. A pattern has been successfully matched if at the end of the sequence of text the automata is in an accepting state, seen here by the state ABCAB. Let's now have a look at the algorithm for string matching. We are passing into the algorithm delta, the transition function, T, the sequence of text, and A, the set of accepting states. This algorithm is very simple. We are stepping through the characters of T one at a time, and passing that character and the current state Q to the transition function and setting the current state Q to the new state. This is repeated until we reach the end of the text. Once we have reached the end of the text, we then check to determine whether the current state Q is in an accepting state. If it is, then we accept the string. However, we must also consider this slight alteration to the algorithm. In this example, we have moved the accept state detection to within the for loop. This is for the purpose of detecting whether some text contains a certain pattern, as opposed to previously, where the algorithm detected whether the text ended with a certain pattern. Let's visualize this algorithm with an example. Here we have a pattern P, ABCAB, and we're going to check for this pattern within the text T using a finite automata. The table below displays input and the current state. Any missing transitions on the finite automata can be assumed to return to state 0. We read in our initial character A and move along to state A. We then receive a B and move along to state AB. However, at state AB we receive an A character which breaks the pattern P. However, we do not return to the start state. This is because we have an A which matches the start to the pattern. So instead we move to state A. We then receive a B and move to AB. We then receive a C and move to state ABC. We then receive an A, move to state ABCA. We then receive a B and move to the accept state ABCAB. Now the pattern has been matched, any further input does not cause any transitions. Let's now perform another example. Notice that this time we are checking to see whether text ends with a pattern P, rather than is contained within it. Our first input is A. A second is B. A third is A. A fourth is B. So far the pattern is successfully matching. However, at input character A, the pattern is broken. But the resulting characters ABA can still possibly match the pattern, so we return to state ABA. However, we receive an A, resulting in 2 consecutive A's, returning us to state A. We then receive a B, move to state AB, input A, input B to ABAB, input C to ABABC, input A to ABABCA, and finally input B to result to the termination state. We can display the automata from the first example as a state transition table. This tells us which state to move to given some input on a current state. To perform string matching with Automata, we need to first create a state transition table. However, this is quite a costly part to the algorithm. For the upcoming algorithm, it is important to refer to states numerically. Consider the conversion displayed here. Now let's look at how to create a state transition function. As you can see, we're passing in the pattern to be found, t, and the finite alphabet, sigma. As you can see, we're looping through two for loops. The first is looping through every state, and the second is looping through every letter in the alphabet. Now this part initially looks confusing, so we'll analyse it sequentially. First, we are setting k to the minimum of n plus 1, which is the length of the text, or q plus 2, the numerical value of the state. Let's now analyse the repeat statement. First, we decrement k by 1, and then perform the comparison in the until statement. This comparison is checking to see whether the first k letters of t is equal to or on the end of the first q letters of t with an appended character a attached to the end. Let's do an example to see this in action. We're using the pattern sequence ABCAB. We're going to assume we're at the stage in the for loop where q equals 3 and the current character is a. Taking the minimum of the two, with n plus 1 and q plus 2, we get k equals 5. Upon entering the repeat loop, k is now set to 4. The until statement is broken immediately, because the first 4 characters of t, t4, which is ABCA, is equal to the first 3 characters of t, ABC, plus the appended a at the end. As we can see, looking at our transition table from earlier, given q equals 3, or in other words, being in the state ABC, given the input character a, we'll move to t4, or in other words, the state ABCA. Let's do another example. Again, t equals ABCAB. However, this time we're going to assume that q equals 2 and the character equals a. k is set to 4, the minimum of n plus 1 and q plus 2. For k equals 3, t3 equals ABC, but t2 equals AB, plus the character a. In this case, ABC is not a suffix of ABA. For k equals 2, AB is not a suffix of ABA. Finally, for k equals 1, a suffix is found. As we can see, given our state transition table from before, given q equals 2, or in other words being in the state AB, given the input character a, we'll move to t1, or in other words the state A. The value of k is calculated for every letter in the finite alphabet and for every state. This allows us to produce a complete and functioning transition function for the automata. Now let's discuss runtime. We have to split this up into two separate algorithms. First, the matcher, which matches the strings, and secondly, creating the transition function itself. The first is fairly simple, a simple for loop that runs 1 to n, giving it a big O of n. However, the second is much more complex. Firstly, the repeat statement has a max of n plus 1 iterations. Secondly, the until has a max of n characters it could iterate through. Thirdly, we have the for loop looping through each character in the sigma. And fourthly, the outer for loop running for each state, giving us a total of O n cubed times the size of sigma. Adding these together, we get the final time complexity, which comes to O of n plus n cubed times the size of sigma.